The topic for today is SPFM or single point failure metric. We're going to look at what the SPFM is, how to calculate the SPFM, and then we're going to look at a real life example of what the SPFM looks like and how it is calculated. SPFM is one of the hardware architectural metrics that is recommended in Part 5 of ISO 26262. Essentially, it is a metric that defines how robust a system is to single point and residual faults. What this metric means is what percentage of the total faults are single point and residual. Essentially, a higher value of SPFM means a higher level of robustness, and a lower value of SPFM means a lower level of robustness. Now, we need to define what is a high level and what is a low level. And luckily, the ISO 26262 defines this for us. And it's defined based on different ASILs. So, for example, if we have a project wherein a safety goal violation is ASIL B, or the highest safety goal is ASIL B, then we need to achieve a single point failure metric of 90%. If it is ASIL C, then it has to achieve a 97% SPFM. And if it's ASIL D, it has to achieve a 99% safety goal SPFM. Now, if in a project there are multiple safety goals, one is ASIL B, and one is ASIL C, and one is ASIL D, each safety goal has to achieve individually a SPFM of 90%. So the ASIL B safety goal has to achieve 90% SPFM, the ASIL C safety goal has to achieve 97%, the ASIL D safety goal has to achieve 99%. So what is the SPFM like? What is it mathematically? There is a formula that is used to calculate the SPFM, and it's essentially this. SPFM is equal to 1 minus sum of single point failures plus residual failures divided by all the failures. You can also define this as the sum of the multiple point plus safe faults divided by all the faults, where lambda here represents the sum of all the faults: single point failure, residual failure, multiple point failure, and safe faults. Now, let's take a simple pie chart to describe all of this. Now, let's say we have a project in which we've done an FMEDA, or you could do an FTA, and then we've identified what is safe, what is not safe, what is residual, what is multiple point. Let's say, for example, we've identified that there is a certain percentage of faults that is safe, either safe by design or safe because of it can be detected by a mechanism. We're going to call them safe faults, or lambda s. And this is represented by this section. Then you can have multiple point faults, which is two independent faults leading to a safety goal violation, and that is represented by this chunk. Then you have single point faults, which is failures of components that do not have any safety mechanism. So it would just go undetected and it would lead to a safety mechanism violation. That's represented by the small section over here. And then you have residual faults. Residual faults are single point faults, a part of which is detected by a safety mechanism and a part of which is not detected by a safety mechanism. The part which is detected by a safety mechanism is categorized under safe faults. The part that is not detected by a safety mechanism goes into residual faults. So all of this together, the entire circle, this represents lambda, the total sum of all failures. Then you have safe faults, which do not lead to a safety goal violation, multiple points which lead to a safety goal violation, single point faults which lead to a safety goal violation, residual faults which also lead to a safety goal violation, but a part of it is detected by safety mechanism. Now, the formula for calculating lambda is equal to lambda SPF, lambda RF, lambda MPF, lambda S. So it's just the sum of all these four. Now, if you look at the formula for SPFM, it is the single point fault metric is equal to 1 minus the sum of single point failures and residual failures divided by lambda. The numerator here is the sum of this chunk here and then this chunk here. This is the residual fault. And then the denominator here is all of it. In this particular example, you'll see that this numerator term is going to be very high because you have a lot of residual faults and there is still a sizable section of single point faults. Almost you could say that this residual fault plus single point fault is about 50%. What that means is this term is 50%, which is SPF plus RF divided by lambda is about 50%, which is 0.5. And 1 minus 0.5, we get a single point metric of 0.5, which is 50%. If we compare this to our target metrics, we see for ASIL B, we have to achieve 90%, and where we are currently is 50%, which is very, very low. So what that means is one of two things can be done. Number one, increase the value of the denominator, or number two, increase the value of the numerator. Now, let's look at number one, which is increasing the value of the denominator. Increasing the value of the denominator would mean that the overall lambda is going to be much higher. This means that the PMHF, which we've talked about in the other video, is also going to be affected. So this is not a good strategy to try to increase the lambda. Instead, what we need to do is to decrease this value. What this means is we have some single point failures which do not have safety mechanisms. We need to reduce that. We need to add some safety mechanisms for some of these single point failures. Number two, what we see is this lambda RF is a big chunk over here. We need to decrease this. What that means is we need to make sure that the existing diagnostics for some of these failures need to be improved such that they are detected and they move over to the safe fault section. So once we are able to move this to the safe fault section, then the sum of single point failure and residual failure is going to decrease. And we want to decrease it so much that this term is, for an ASIL B safety goal, this term is at least less than 0.1, less than or equal to 0.1, because if it's less than or equal to 0.1, then this value ends up with 1 minus 0.1, which is 0.9. 0.9 is equivalent to 90%. What this now means is if I have a failure in my system, 9 out of 10 failures are either safe failures or multiple point failures. And with the multiple point failures, the risk is very low. So 9 out of 10 times, it's a safe failure or multiple point failure. If I'm able to increase this to 99%, it means 99% of the times my failures are safe or the safe failures are multiple point, in which case the risk is very low. That is the significance of the SPFM. So the SPFM, if we go back to the definition, is a metric that defines the robustness of an item to single point or residual faults. Higher the SPFM means the better is my system to, to reject a safety critical failure. Lower the SPFM, it means there are a lot more failures in my system that can lead to a safety goal violation. Next, we're going to look at an example in a concrete project to see how to calculate SPFM.